So before we get straight into the lecture stuff and answering questions, I wanted to point out a couple things. One is a big kind of adjustment. If we take a look at week 6, you can see that there's practice problems within the Canvas. Okay? And there's this one that's called Practice Open Edit, which will take you out to a Google Doc. That Google Doc, theoretically, if I've got it set up right, anyone who has access to the link is now an editor. So what you can choose to do is come in and put your answers into it. Right? If you put your answers in, what I'm going to try and do is now go back and check and verify that answers have been submitted. If answers have been submitted, I will respond whether you were right or wrong and provide some feedback on how to change your answer to make it more appropriate. Does that make sense? All right. The point of having it open edit is that way when one person does it, everybody can benefit. So the hope would be you would all be contributing to these open edit documents, and then I will be going through and checking them and providing feedback. Right? It is new. This one's officially week 6, and I forgot to mention it. So I don't think anybody, it doesn't look to me like anybody put anything into the document here. But it is a Google Doc. You can take pictures with your phone and upload images from your phone, just like we do for the lab. Right? So you do not have to do it. I will try and check at least once a week for all the documents that are open edit, right, that should be linked within Canvas. And I'll provide that feedback. If you don't want to put your answers in there, okay, there's a couple things that I'll point out. Number one, it's anonymous. The only way someone would know that it was you making the edits is if you actually signed in to the document and said, this is Kimball, and I'm saying all these things. Right? So it's anonymous. Who cares if you're right or wrong? You're at least providing that feedback and trying to come through an explanation. You'll then get feedback from me saying what's potentially wrong within that, okay, where your thought process went, okay, or where it might have gone and where it needs to be redirected. Does that make sense? Right. This is something that I've used for other classes, and they said it was hands down the most important and valuable tool that they had, because they got that feedback back on everything.
So for individual or everybody in class?
So everybody in class has access to edit this document. Officially, everybody in the world has access to edit this document. Okay, so what will happen, so I'll pull up a different document, different class. They're just slightly different because it's a exam, or an old exam. Come on now, how are you doing? So there was a question, circle the strongest species, which theoretically this unit you should be able to do, okay, though it is technically kind of a harder question. And someone went through and provided what they thought was the answer. Okay. I will then follow it up with a Mike says, okay, good job, I think you did it right. Okay. Sometimes it's just hey, I think you did it right, let's just move on. Other times I might point out that when you look at these questions, they're just a question. You should be addressing the content of the question, not the question itself. Because when you get an exam, while you might see the same question, there's probably a higher probability you see a slight variation on it. So if you understand what it could be changed to, you have the potential to now be able to answer almost any question I throw at you on an exam. So if we go through this, what you'll see is a lot of, usually students pick something other than red, okay? So it'll be blue or black. Ideally it's a color so that it stands out to me so I know an edit has been made, okay? And all I go through and do is I look for that color and I see if I had a red response. If I didn't have a red response, I move on. Or I don't move on, I now answer that question, okay? So it is something you do not have to do. There are no points assigned to it. It's just something that you can do to help get some of that kind of feedback. You don't want to post to it, that's fine. I'll still give you feedback, you just have to talk to me. Right? That's now much more individual, and that doesn't get as much of the kind of shared community building that you can get through this document. Does that make sense? Okay. So So that's the intent behind those. That's why they are open edit, is so that you could go in and you can submit your answers. Okay, within those, okay, for the week 6 one, none of those were short answers, so you had to provide kind of some kind of explanation behind why you were doing what you were doing. When we move to the week 7 one, it's a lot of multiple choice. If you just tell me the answer is A, I'm gonna be like, no, I'm not providing feedback. Because the point isn't to figure out what the answer is, because you go, oh, well, it's not A, I'm gonna say B next. Does Mike say it's right now? That's not the point. The point is to explain why you think it is that answer. And then what you'll get feedback on is the critique of your explanation. Okay? And if you don't have an explanation, try your best. Guess and then say, well, this is why I think this is going on. That's going to provide something for me to look at to be like, okay, here's where I think you have a conceptual miscue. That needs to get fixed. Okay? When you don't know the answer or have low confidence, you know something, work with that something, and maybe you can find out why there's a larger issue going on. Kind of, sort of? Okay. Just starting the class, do we have any questions? We're now sitting in week 7. We've got a lot of play posits, the reactivity of things, and acid-base. The advanced is a question mark. It might be kind of advanced. Okay, and we can go through that. Hopefully we'll get to that this week. Next week, for sure, what we're going to be looking at is what are all of our reactions? What are the basic components behind those reactions? And then how do those reactions work or how they run? Okay? So you could say, well, I'm going to go grocery shopping versus I'm going to go to school. Those would count as reactions. But do those reactions run the same way? Do you have to get dressed in both? Probably. Okay. Do you have to drive in both? Okay. State of Arizona? Probably. Okay. But I can say for sure where I used to live, I did not drive to the grocery store. When I needed to get groceries, I walked out the front door, across the road, and I was at the grocery store. Okay. Best way to live in my life. I'm so pissed that we moved. Okay. But that was phenomenal. That is a different mechanism. That's a different how that reaction happens. And we talk about chemistry, we have reactions, and there's the how those reactions happen. So those two kind of things scaffold together. If you understand those things, all the reactions, which is the rest of the semester, okay, the second half of the semester, is now just repetition of those parts. So if you're strong and pick up those parts, it means you don't have to memorize as much later on, which is where the meat of organic chemistry really comes in. It's now, well, here's a new reagent, what does it do? 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 And if you're like, well, that's kind of repetitive, that is the vast majority of organic chemistry, right? And you either memorize all of those pieces, or you understand where the structures are located and how they potentially react, which is what Unit 1 was. What are the structures? Unit 2 is now how can they potentially react? Unit 3 and 4 are now just here's all the reactions. Okay? And before we get too panicky about that, we don't do all of the reactions. Okay? We take kind of select examples, theoretically the simpler examples, okay, of those classes. Okay? So the reactivity of things is something we are going to constantly come back to. Okay? The acid-base advanced is now looking at a specific chemical reaction. When we look at our mechanistic steps, which is a video next week, that's the how each of those things happen. Does it look like a lot? Hell yes. Okay? Because now what we do is take what we understand about structure and now start to say how those things can change. And that is a pretty big leap. But a little bit of practice and you should be pretty awesome at it. Okay? Questions? One more question for you. Has anybody attempted the play posits for this week? The reactivity of things in the acid base?
I did, and it wasn't really letting me advance through it.
Yeah, that's exactly why I was asking.
Yeah.
Okay. Play posit is doing something weird. I'm in conversations with play posit to figure out what's going on. So yeah, if you attempt any of the play posits right now, they aren't going to work. The very first question is going to pop up. It prevents you from moving forward until you answer it, but then it says it won't acknowledge whatever you answer. No idea why.
I did it, I think this weekend, and
It was fine this weekend.
yeah. I don't remember if it was Saturday or Sunday.
I don't remember when my first email complaint came in. If it came in on Monday or if it came in over the weekend. So,
I think I did it before she did it, so,
Oh, before that?
yeah. So
Yeah.
it might be fixed now.
okay.
I don't know.
It's worth looking at. That content is something you need. Okay, so minimally what I would recommend you do is scroll to the bottom of the assignment. So if we look at the reactivity of things, play pause it may not work. And I'm trying to figure that out. But at the bottom of the assignment, you get the YouTube video. So you can click the YouTube, watch the YouTube. You're not going to get credit for having watched it. Okay. I may end up just giving everybody credit for it anyway, depending on what play pause it comes back and tells me, okay, on what's going on with it. But until they respond, I don't know why it's wrong or why it's not working. You can keep trying periodically, but you should still be advancing that content. You need to watch those. Make sense? Okay. Any other questions? Okay. Where I believe we ended Monday was looking at this slide. Okay. Did we actually predict which one had the higher melting point for number one? Yeah, which one was it? B. Why did we say B had the higher melting point? Yeah. Okay, so this was, oh, we did talk about it because I talked about the little kids and Dwayne the Rock. Okay. I talk about him all the time. He should, give me points. I'm helping his street cred. Okay. So yeah, it's the same force, but now the amount of the force contributes. The same thing officially happens with solubility as well. Like dissolves like. You look, do they have the same force? Okay. But then what's the amount of that force present in that molecule? So if we were to look at, actually, yeah, we're just going to do this. A slightly different example. If we now looked at solubility, so we can delete all that. And I wanted to know if ethanol dissolves in water. Okay. Well, solubilities like forces dissolve like forces. I'd look at water and I would say it has what force? Hydrogen bonding. I look at ethanol and I say it has what force? Hydrogen bonding. So is hydrogen bonding similar to hydrogen bonding? Yes. So what does that mean? They dissolve, they mix. Okay, great. Seems simple enough. Okay, but what happens if we now change this question and I do this? Well, that's not very much of a change, so let's do a whole bunch more. Those may not be the prettiest, but those are little zigzags representing carbons as we go, right? Okay, what's the strongest force in the blue molecule now? What's the strongest force?
It can still be hydrogen.
It's still hydrogen bonding. Okay? And so if we were to just say, well, should these mix? We say, well, hydrogen bonding is the same as hydrogen bonding. Shouldn't they mix? But if we test it, okay, to Sydney's point here, it doesn't mix. Well, why not? Okay? Solubility isn't just about the strength of the force. We also have to take other things into consideration. The other things we have to take into consideration is the amount. Okay? So that when I look at that blue molecule, yes, it has hydrogen bonding down here, but what else does it have? All of that is going to be what type of bonds is all that circled in purple? this goes back to Unit 1. Do we recognize what those zigzags mean? Yes, okay, then tell me.
You were just asking like what bond it is.
Yeah.
Carbon to hydrogen. Yeah, carbon to hydrogen.
Okay, I'll give you carbon to hydrogen. Is that the only bond that's represented in there?
Carbon to carbon.
Thank you, carbon to carbon. Both of those bonds are what type of bond? They're non-polar covalent. Okay, and I may not have heard your non in front of that, so let's just say you said non in front of that, right?
Yes.
Yeah. Okay. Okay, so that's the definition of non-polar covalent. The same element bonded to the same element, so carbon to carbon, and carbon to hydrogen. That's the raw definition of non-polar covalent. Okay, if we have non-polar covalent bonds, what kind of force does that lead us to? London dispersion forces. Okay. So now when we go through to consider that black box, what's the dominant force within that box? And we note a subtle change in the language. I'm not talking about just the raw strength of force. Hydrogen bonding is still absolutely a stronger force than London dispersion, but the dominant force is now taking into consideration something else. It's taking into consideration the amount. So that when I now look at that black box, while it has both hydrogen bonding and London dispersion, the dominant force, or the thing that most represents that molecule, is London dispersion. Is London dispersion similar to hydrogen bonding? No, which means they don't mix. Okay? So when we talk about kind of solubilities and melting points and boiling points, there are things that always kind of tweak the rule, okay? And ultimately, it's not a rule, it's the primary characteristic. It's our first approximation, okay? We could go through and separate people in the class based off of gender as a first approximation, but we could probably separate people further after that, okay? And further after that. And it's gonna come down to some small characteristic that's ultimately allowing you to make that differentiation. Is that differentiation useful? That's another question altogether. Okay? In this particular case, we want to know, do they mix? So if the differentiation allows me to predict that they mix or they don't mix, yes, the differentiation is useful. Okay? If it doesn't allow me to predict that, then that wasn't a useful differentiation and we ignore it. Okay? So for instance, we could say they're different because one has carbon and the other does not. Okay? That is a way that they are different. Does that explain why they don't mix? We might say, well, yeah, doesn't it? Except that if we go all the way back down to ethanol, does ethanol have carbon? Yeah, it does. These points were carbons. So saying I have carbon means they don't mix isn't a useful differentiation. So it's trying to figure out what those differentiating factors are, and we start with kind of primary characteristics. That's where we look to the strength of the force, because that's our primary interaction. After that, we can start to look into amounts. We could also factor in structure. Okay? From the erasing everything is a bad idea. Now everything is okay. For those of you in the lab, you were asked a question about THF versus diethyl ether. They have the exact same number of carbons. They have the same number of oxygens. There's just a 2 hydrogen difference. Does hydrogen really make a difference? No, we could go back to ethanol and water for that comparison. And I added a whole bunch of hydrogens different in ethanol in comparison to water, and they still mixed. So the hydrogen count wasn't a relevant difference. So if we were to ask ourselves, how would these interact with, say, a third substance, water? How do we decide that? Well, we'd start with forces. They have the same forces, dipole, dipole. Okay. We could look at amounts. They have the same amount of forces. Okay. So we might say, well, they're the same. They both have the same solubility within water. And yet, when we test it, we find out this one is extremely miscible, as in it mixes, and this one is immiscible. It does not mix. Well, is that now an exception? No, it just means we didn't look at a differentiating factor that contributes. What's the next differentiating? What else do you see that's different between these? You can go all Taylor Swift on you, right?
This shape of the molecule.
Yeah, the shape of the molecule. We're looking at a cyclic structure versus a chain. Okay? How does that change how that molecule can interact with the world? Okay? Okay? What can a chain do? Can a circle do that same thing? So that restriction in motion is now changing its ability to interact with water. Okay? That subtle change in structure turns into a massive change in solubility. Okay? So should we always start with structure? No, we should start with the primary, which is the strength of the force. And you slowly dig down deeper and deeper and deeper into that differentiation to try to explain what's happening. Kind of, sort of? We will do similar things with a much better effect when we talk about the reactivity of molecules. Okay? Solubility and melting point is a little bit more of an art form and a guess. We don't need to get super nuanced with it, because if I want to find out which of these compounds boils at a lower temperature, it's really easy for me to test. I heat them up and see which one turns into a gas first. Done. I've got it. So I have confirmation of that very fast. Same with solubility. Okay. Well, I don't know which one dissolves. Well, add water, see what happens. Oh, they dissolved. Okay, that dissolves. Okay. There's a very fast confirmation of that, and because there's such a fast confirmation experimentally, we don't need a rigorous theory to help explain it, because the experimental does it on its own, effectively, instantaneously. Where we need more rigorous theories is when the experimental isn't a matter of seconds, it's a matter of hours or days. Okay? Some other repercussions that we can get at, okay, which we just addressed within this, your melting points, okay, and boiling points, as we talked about in lab, is the energy necessary to cause that phase change. Okay? What's resisting the phase change? Why are solids staying a solid? What phase have I shown here? A solid. How do you know that?
Atoms are close.
The atoms are all close to each other. Well, what's holding them together? Okay? And this is where we now fall back on the terms that describe it. What's holding them together is the stuff that's happening in between the individual molecules, okay? Which are the forces. You'll oftentimes hear people say, oh, well, it's the bonds. Bonds aren't holding that together. Bonds are what's holding that red box together as a box, not as four lines. So when we talk about phase transitions, we aren't breaking the molecule. We're breaking the forces that connect those molecules to each other. Okay? It's a subtle change in the language, but it's a very drastic and significant one. How drastic and significant? There was allegedly a study done about graduate students to some Ivy League college, okay, where they said, okay, if we take water and I heat it up, what happens to liquid water when I heat it up? Boils. What does that mean?
Gas.
What's that?
Gas.
Turns into a gas. So we say gas. Right? And I don't know how the question was phrased, okay? But the results that they got back from students was what was the identity of that gas? And what did they say it was? Hydrogen and oxygen. Not water, Not H2O, but the hydrogen separated from the water. Why? Probably because the language is so powerful that when we talk about heating things up, if we talk about breaking bonds, what happens to the bond connecting the hydrogen to the oxygen? Well, we'd say it breaks. And we get free hydrogen atoms and free oxygen atoms. Is that actually true? No. We maintain the molecule of water in the gaseous state. These are graduate students. These are students that went through 4 to 5 years of an undergraduate education, and they can't explain what happens when you boil a liquid. Language is very powerful, and that's why we have to be very careful when we talk about bonds versus forces. Forces are what's explaining our phase transitions. Bonds is what's explaining our chemistry. Kind of makes sense? So for the record, when we look at the gas, what is the species that's in the gas? It's H2O. And water is an extra nasty one, because when we say water, what do we naturally imply? The liquid. Okay? And it's not a liquid, it's a gas. So there's all sorts of other kind of secondary things that could be contributing to why those allegedly very advanced students were screwing this up royally. Okay? And I use that as an example to point out that it isn't as straightforward as I might make it sound. Okay? So it is kind of a complex concept. That's what I think I was going for. Okay? And it's easy to goof. Okay? And if we go through with this, we can now start to answer questions. If we have a species with a higher melting point or boiling point, what does that suggest about that individual molecule? It has stronger forces. Okay? So I can now predict something about that molecule just based off of its melting point and boiling point. That's pretty powerful. Okay? If we continue on with that, oops, because I still have this open. We could go through and use solubility, the ability to mix things, the things that are helping this. If you have similar forces, okay? What hurts it? If they're different forces. Are there other things that contribute to solubility? It's really a lab question. Heat. Because what does heat do? Breaks the forces. And if the forces are broken within an individual substance, it's easier for them to mix because you've already broken the force that was holding them together. Okay? The next kind of big thing that can kind of come out of this, whoops, where's my image? Oh, because I moved into solvents. Okay? So our observables that we're talking about here are ultimately not our chemistry. Okay, so I put the not in kind of the wrong, or the quotes in kind of the wrong space. When we're talking about these physical observables, this isn't talking about chemical bonds per se, we're talking about chemical forces. Okay? And yes, those forces have to come from somewhere, they're coming from bonds, but we have to be real clear that what we're talking about for our individual physical states is the strength of the force between those molecules. None of our phase transitions are actually breaking chemical bonds. Okay? To break a chemical bond, we'd have to take it to the next step. But before we can even get to the next step, we have to address kind of the next thing about our chemical reactions. So first and foremost, what we would do is mix multiple things. If I want to mix and do a chemical reaction, I might mix gaseous methane with liquid water. Okay? And for a chemical reaction to happen, what must the methane do with the water? That's a hard question, so let's change it to people. To produce babies, what must the individuals do?
Procreate.
Yeah, how? Don't get too graphic on me.
Come together.
They must come together and interact. If they never interact, if they're in separate rooms, separate states, you can't generate procreation. You can't get a chemical reaction. So when we're talking about mixing chemicals, It's not just, oh, I mix water with methane and ta-da, I get a product. I have to consider how they're mixing, where are they located. And if we look at gaseous methane versus liquid water, those aren't evenly mixed. This is a gas, this is liquid. Those are in different phases, which means the only place they can interact is on the surface of it. Okay? The surface of the gas bubble. So if we were to look at, say, that gas bubble of methane, we're going to have CH4s all around this. Right? And inside this. And if we want to interact this with water, okay, as a liquid, the only CH4s that can interact with the water are the ones on the surface. The ones that can't interact are located on the inside because it's in a different phase. Okay? So multi-phase chemical reactions slow down. They slow down because we've put our chemicals, we've divided them through a phase barrier. It's effectively putting a wall in between, okay, our couple and saying we'll make babies. That's going to be really hard to do, okay, because the wall prevents that. Okay? So the first thing we might go through and do as a scientist would be, let's make sure that there's no barriers. And if there's no barriers, what I want to do is remove those phases, or at least put all those phases into the same system, in the same place. So that now when I look at my chemical reaction, I've got my H2O scattered around as before, but now the CH4s are also equally scattered around. Does that make sense? So what's different about our scenario, we'll call it A, versus our scenario B?
You have more of a reaction in scenario B?
I can get more of a reaction, but why?
Because they're able to actually interact.
Why can they actually interact?
Because they're the same phase.
They're all in the same phase. We could use a word to describe that. Technically, you learned it way early on in Gen Chem, Chem 130. This is a homogeneous system. This is a heterogeneous system. Okay? And sometimes we can't get our chemicals to come together homogeneously. Okay? Perhaps because they have different forces. Water's hydrogen bonding, methane is London dispersion. So those may not mix. So what we might decide to do as scientists is add something else into this system. This something else helps to bring those chemicals all near each other. So we make the situation more complex, but the hope is we minimize this bubble system. That thing that we're adding is to make sure we get a homogeneous system. Right? Our homogeneity is ultimately referring to our phases. So which phase should we target for our homogeneous system? Should it be, and when we talk about solids, liquids, and gases, we're typically talking about those as pure substances. Now we're talking about them as mixtures. I just want to be kind of clear on that statement. Which phase is best for us to run a homogeneous reaction? Solids, liquids, or gases?
Liquid. Gas.
You said gas, you said liquid. Okay. Does anybody want to say solid? Good. Solid's the worst choice. Okay? Because solids by definition have stuff stuck in the middle. Okay? There isn't anything you can do about that. If we move to the liquid phase, what we're assuming is all those particles are equally mixed around, okay? And it's homogeneous. But we get that same situation in gas. So why do you think gas is better?
I guess because we're trying to achieve a homogeneous mixture, right?
But as we just said, you can get a homogeneous mixture with a liquid.
But we just have to add, I guess.
Okay, so there's a possibility. You might have to add something in there. And if you're adding that something, what does that do to those potential interactions?
Inhibits them.
It inhibits them. Okay, so going to the gas phase makes sense. Okay? So Sydney, why do you think the gas phase is awful?
I didn't say it was awful.
Fair play.
I just would think it would be harder to, like,
That's a good start.
contain.
Ah. If we think about our gas phase, what happens with our gases?
Gas.
Their properties, they fill whatever volume they're in. Which means if we're going to do chemical reactions on the gas phase, okay, and I just want to say, oh, look at this gas phase reaction happening right here. It's not going to happen right here. It's going to happen in the entire freaking room.
In your
Okay.
lungs.
That could be very dangerous towards our lungs. Well, oh, okay, well, Mike, I'll just seal the container. Okay, but now you have a sealed container with gases in it. And if we change the reaction, heat it up, the gases start to move more or potentially produce more gases. And if we have gases expanding in a sealed container, we have just created a bomb. Yes, that's generally speaking a bad thing to work with. Okay, so while the gas phase is probably the best scenario, okay, the issue is that it's very hard to control and almost always it turns into bombs. Okay? So we don't typically like bombs, we instead like liquids. Okay? I use the word liquid saying it was a mixture, okay, really because I wanted to use solid, liquid, and gas. Okay? When we talk about liquids as mixtures, they aren't liquids because liquid by definition is a pure substance. What we're talking about now is solutions. Okay? So we would take our chemicals and add them to a main solvent, a thing that would allow them to mix with each other. When we think about all the Gen Chem reactions you did, you've done tons of Gen Chem several Gen Chem reactions. What was the solvent you used? Yeah, you used water. Okay, so water's a great solvent. Okay, in fact, most of the world that we work with, okay, on an everyday basis is using water as a solvent. Right? The problem with organic chemistry is that if we look at our organic molecules, what did we say was an organic molecule?
Carbon.
Carbon and officially with hydrogens. Okay, so let's just pick a nice zigzag structure there. Would I expect that molecule to dissolve in water?
Yeah.
No. That molecule, as our standard organic example, is full of London dispersion forces that should not mix with water, which means water is not a great solvent for organic chemistry. And instead, what we end up picking is other liquids that can do the same thing. But it just ultimately just has to be a liquid. Okay? But now the question becomes, what are those liquids, and are there ways that we could potentially classify them? Okay? So this is where you will typically hear reference to this statement of polar versus nonpolar. So those people in lab that were trying to identify solvents or compounds, oh, it's a polar compound versus a nonpolar compound. It's a horrible term to use because we can't define polar. Right? And if you go out into actual research and you say, well, this is a polar solvent, depending on how you test and define polarity, you can change a solvent from being polar to nonpolar. That's pretty gross. Okay? You shouldn't be able to do that. And that's because that term is too vague and it doesn't allow us to really manipulate and understand it. So within this context of this class, we use the terms polar and nonpolar to mean something very particularly. We're talking about a polar covalent compound or solvent versus a nonpolar covalent solvent. Okay? So this is going to push back to the bond types. Why do we not look at the ionic substances as our solvents?
Because they're a less popular force.
No. Why do we ignore the ionic compounds as a solvent?
Can you not have an ionic compound as a liquid?
There it comes down to. Our ionic compounds have very strong forces, which means, what phase are they typically?
Solid.
Solids. The whole point is to have a liquid. So we very rarely see ionic liquids. Okay? So that's why it's excluded from our solvent terminology. Does it exist? Yes, it's a very active area of research. There's lots of people studying it to see how that ionic substance or how an ionic solvent would change overall chemistry of a reaction. Okay? Maybe in 10 years, people will have to learn that. You're not there, don't worry about it. So our focus is we're looking at polar covalent compounds versus non-polar covalent compounds as our solvent terminology. Okay? And because we're lazy, what do we do with the word covalent? We just get rid of it. Okay? So we can talk about our solvents as polar and non-polar, and what we're referencing that to is towards their bond characteristics. That gets a little bit dodgy because we're talking not about their bond, but more importantly about the forces they exert, okay? Which is where the next level comes into this. If I look at a non-polar covalent compound, carbons and hydrogens. If I look at polar covalent compounds, I could look at, I'm going to draw methanol. Not methanol. Sorry. I'm going to draw acetone. And I'm going to draw water. But we said water we don't necessarily like as a solvent. That doesn't mean it doesn't fit these definitions. Okay? So I've got these three compounds. How would they class into my polar versus non-polar solvent? Well, it's based off of the bonds, right? What bonds are present in my methane? Non-polar. What bonds are present in my acetone? Okay, polar covalent. We do have non-polar covalent, but the polar covalent being the stronger force dominates our overall system. And then in water, we have polar covalent. Polar covalent, again, because oxygen to hydrogen. Okay, this should create an issue. Okay, water and acetone now have the exact same definition. They're both polar. Okay, but do they exert the same forces?
No.
No. Since they exert different forces, we now need to be a little bit more careful in delineating our labels out of this. Okay? So what do we mean by that? Water has the ability to do hydrogen bonding. Okay? So I can call water a polar solvent, but I now also want to draw attention to the fact that it hydrogen bonds. So I could call it polar hydrogen bonding. Everybody happy with that name? Shouldn't be. That's an awful name. It's a mouthful. I don't want to say that. Okay, so what do we use instead? We call water polar, because that's where it comes from, and we add this word protic. What the heck is protic in reference to?
Can accept hydrogens.
Sort of. Technically the other way around.
Can donate
Hydrogens.
hydrogen.
Protic for proton. What was a proton? Proton was just the positive particle within our nucleus, right? If I take a look at the hydrogen atom comes in with one proton and one electron. Where's its one electron? In the bond, which means how many electrons are chilling around this H? None. So it's effectively just a proton. So we can call it a protic solvent, or polar protic. If we move to the next substance, is it protic? Does it have the ability to give us this positive hydrogen? There are a bunch of hydrogens there, but are those next to an electronegative element, like oxygen, nitrogen, or fluorine? No. So that one is polar, but it is aprotic, where the A is in reference to a not. Okay? What happens with the nonpolar? Should we be adding this new term to it?
It's just non-polar.
Okay, but is it protic or aprotic?
It's non-polar.
Answer my question.
It's neither.
It's not true. It's absolutely one of them.
Is it aprotic?
It has to be aprotic. Because if it was protic, it wouldn't be nonpolar anymore, it would be polar.
Doesn't the question ask on the homework?
We're gonna come back to that.
Polar product or
Okay. So now we can think about all of these terms that we've used to segregate out our possible liquids, our solvent, the thing that would dissolve everything. Okay? And to your point, if it's nonpolar, what is it by definition going to be?
not important.
Aprotic, which means, what could I do with the word aprotic? I can get rid of it. I don't need to include that anymore because it's implied in the aspect of it being nonpolar. Okay? We could go over to here. Okay? If it is protic, what must it be by definition? Polar, which means?
Hydrogen bonding.
Yes, similar to our concept over here. If it was nonpolar, what does that mean about the next word? By definition, it must be aprotic. If I look at protic, by definition, it must be polar, which means what can I do with this name?
Get rid of polar.
I can get rid of polar. Okay? So we could now create 3 categories. We could call a solvent protic, we could call a solvent nonpolar, and we could call a solvent polar aprotic. Okay? Could we do another simplification on the polar aprotic?
Yeah, because by protic, by definition, doesn't necessarily mean. Or no, never mind. I'm looking at the forces.
I would, and it does come back to forces. Aprotic means you can't have hydrogen bonding. Right? So it's just another name of labeling it. If I call polar protic just protic, and I now say I have a polar solvent, is it a protic solvent?
Not necessarily.
Depending on what you decide is your classification, you could say it's absolutely not protic. Because if it was protic, I would have fucking said protic. Okay? So if I say polar solvent, it already excludes the protic category. It means I'm not looking at this one. And if I call it a polar solvent, it by definition can also not be the nonpolar. So I could go through with that middle category and I could just say it's a polar solvent and I could drop the aprotic term from it. Okay? If I chose. Similarly, I could do the same thing with the aprotic word. Because if it's aprotic, it's definitely, well, so this becomes problematic. If it's aprotic, it's not going to be protic, so it's not that polar category. If it's aprotic, and I think back to the nonpolar category, I already ignored the aprotic there. So if I'm saying the word aprotic, it must not be in reference to the nonpolar, which means it must be polar. So I can use either polar or aprotic to describe this middle category, okay, with a little bit of reasoning to exclude the other 2 categories. Do you want to deal with reasoning or not?
No.
No? Okay, you got 3 categories. There's the terms. Protic, polar aprotic, and nonpolar. Those are your categories. All right. So when you go online and hear reference to polar or nonpolar, ultimately what they're trying to do is drop it into one of these buckets. Okay? And this is why referencing polar and nonpolar is a bit weird, because the polar bucket is both of these definitions. The nonpolar is always on its own. Does that make sense? All right. So when we go through and look at chemical reactions, we will add solvents into our system. The point of that solvent, at a minimum, is to bring all of the chemicals together to make it homogeneous. Okay? Which means the solvent must have characteristics of the intermolecular forces of all of my chemicals. And if it has those characteristics, we increase the odds of bringing the chemicals together to actually make the chemical reaction happen. Kind of, sort of. That's its primary role. It has secondary roles because the secondary roles can come in when we look at how the chemical reaction happens. That's more nuanced. I'm pretty sure we don't talk about that yet, so I won't stress about that yet. Kind of, sort of? Okay. Oops, went the wrong way. Whoop. So if we were to look at those 4 solvents, what would we label them? So our buckets, we have protic, we have polar aprotic, and we have nonpolar. Those are our 3 buckets. I'm going to call this A, B, C, and D. What bucket is A? To be protic, what must it have? Hydrogen bonding. Do I have hydrogen bonding on A its own? Do you have a hydrogen bonded to oxygen, nitrogen, or fluorine in A?
I guess it's implied, right?
Where is it implied?
Would it be the double bond or not connected? No, because that'd be carbon.
Okay, so this is a carbon, yeah. Okay. And if there was a hydrogen connected there, would that be protic? No, because protic meant hydrogen bonded to oxygen, nitrogen, and fluorine. So if I put a hydrogen there, it's not going to make it protic. Can I put a hydrogen there? No, why not?
They have 4 bonds.
Carbon can only have 4 bonds. It already has 4 bonds. I can't put a hydrogen there. Okay. How about the oxygen? Could I put a hydrogen up on the oxygen? Why not? This hits a little bit of a weird gray area. You actually asked this question.
Yeah, oxygen has implied lone pairs. Yeah.
The oxygen has implied lone pairs, so when it is drawn in its neutral state, that's its final structure. Does it have its octet? Yeah. Okay. And then the follow-up that we had, which I got to admittedly a bit late, okay, because we imply lone pairs on oxygen, nitrogen, and all of your halogens, what are typically referenced as heteroatoms, not carbon and hydrogen, you cannot imply hydrogens on those atoms. Because if you are you implying the hydrogen or are you implying the lone pair? It's vague, you can't tell. So when we talk about heteroatoms, you can imply lone pairs, but you must be explicit with the hydrogens. Which is why when we draw water, do you ever see me just draw O? No, why not? I have to be explicit with the hydrogens. Okay. Same with methanol, ethanol, all of those other kind of things. So what does that mean? Is there a hydrogen on that oxygen? Nope. And if there's no hydrogen there, it's not protic. So the oxygen can't have a hydrogen. That carbon can't have a hydrogen. Can you have hydrogens down here? Yes, in fact, you absolutely do. You have 3 on each of those carbons. Does that make it protic? Protic must mean hydrogen bonding, and to be hydrogen bonding,
Have a hydrogen readily to donate.
HO.
you have to have a hydrogen bonded to oxygen, nitrogen, or fluorine, which comes back to its ability to donate because oxygen, nitrogen, or fluorine are so electronegative. What have they done to the electrons in the bond? They took them away. That's why the hydrogen could be donated to something else, which means A is polar aprotic. I don't feel like writing it all the way out, but I'll color code. Kind of make sense? How about B?
Protic.
This should be protic due to the UOH out there. Okay. Would we expect this one to act as a fully protic solvent? I know it's a weird question. See what you can do with it. You're saying no. Okay. That's a confident answer. Why?
It's like that example that you did earlier with all the
we have a bunch of carbons out there, and if I was actually going to color code this a little bit better, we have a bunch of those carbon hydrogens out there. So while this molecule should be classified as a protic solvent, it's got a lot of nonpolar characteristics associated with it. So this solvent is kind of, let's go with ambidextrous. It has characteristics of both those categories, both polar and nonpolar. How about the next one? C. Protic. Is this one as nonpolar as B? Still has just carbons and hydrogens there. But it has fewer, right? So while it does have some nonpolar characteristics, those nonpolar characteristics might be a little small. And its now dominant force is probably going to be protic. How about the last one? Straight up nonpolar, no questions. Make sense? Think we got it? Let's put it all together. We could turn this into a quiz. We're not going to do it as an actual quiz. It's just not worth the trouble. Okay. But what I want you to do is go through and take a look at question 3. Okay. At home, you can go through and do 1 and 2. So I won't erase that yet. But what we're going to do is just look at question 3. So what question 1 and 2 are saying is take a look at just the solids, okay, and rank them from highest melting point to lowest melting point. What dictates high versus low melting point? Their forces. Okay? Having a high melting point means I need to add a lot of energy, which says what about my forces? These are strong forces. These would be weak forces. So what you should be able to go through and do would be to say, come up with some kind of ranking system where you're saying, I don't know why I picked red. Okay, we could go through and do something like this. 4, 2, 3, 1. From highest to lowest. So 4, we're saying, has the highest, strongest intermolecular forces. Okay, and 1 has the lowest intermolecular forces. Part 2, or question 2, if you will, says to do it now for the bottom. Okay, and we do the same kind of thing. We could go through and say, I want to rank based off of strongest to weakest. So we could kind of arbitrarily go through and just kind of pick a random order, and we might get something like that. Whoops, I missed my... Right? Does that make sense? So that's what question 1 is asking. 1 and 2. What I want you to do is look at question 3. Right? And I'll give you a couple minutes to work on that. Okay? You can raise your hand if you've got questions. I'll probably come around and pester you anyway. Okay? But we want to try and figure out, okay, which of these are going to make a homogeneous solution. So do I think mixing 1 with A would make a homogeneous solution? Okay, so if I'm asking for what are homogeneous, the homogeneous, if I said 1A, is that a good choice? Okay, and I should go through and do it for each of the compounds, we'll say of the solids. Okay, see what you can come up with. I'll pause the recording. What do you guys think?
3 and A.
Okay. So 3 and A. That was a real loud first jump. Why?
Because they both have London dispersion forces,
Okay.
and then dipole-dipole.
Okay, cool. Can you tell me what forces you see in B?
Both. And hydrogen bonding.
Okay, so you're saying 3 should not dissolve in B because,
Wait, I didn't say that.
well, you didn't tell me 3B. You told me 3A. So why did you not tell me 3B? Did everybody get what I just did? Kind of flipped the script. Okay. By you not pairing 3 with B, you're saying that's not a valid comparison. Why?
I haven't gone that
That's a fair answer.
Because it does have the hydrogen bonding in the other structure.
Okay. So you can make the argument that 3 should not pair with B, even though it has the London dispersion forces, even though it has the dipole-dipole, it also has hydrogen bonding. 3 did not have hydrogen bonding. Okay? So there's a slight difference in the intermolecular forces. That difference is what you're using to say it shouldn't dissolve.
And it wouldn't? That's the answer?
So this becomes a fun one, because everybody goes, well, what's the answer? The answer that I'm looking for is your explanation behind why you're picking these. That's what we're driving at. Okay? Because to decide whether it does or not, what do?
Look at the forces.
You test it.
Oh.
Solubility is very much a ballpark art form. We're choosing it to figure out and saying, well, I think this solvent's going to work well for my reaction because they have similar forces, and then I test it. Oh, dang, it didn't work. Now I choose a different one. Okay? It's a very kind of guess and check kind of approach. But you're limiting your guesses, because if we look at the amount of solvents, we're probably in hundreds or probably thousands of solvents. You don't want to guess and check 1,000 solvents. You want to guess and check maybe 10.
So would 2 and C?
Okay, so now you're just jumping ahead. So would 2 work with C? Why?
Well, no, I'm asking because they have like all the same forces, but 2 has more London dispersion forces.
Okay,
So would that make
so
that
would 2 and C work? 2 has London dispersion forces, C has London dispersion forces. Everybody agree? 2 has hydrogen bonding, C has hydrogen bonding. C also has a dipole-dipole with the carbon-oxygen double bond. Does 2 have a dipole-dipole?
Yes.
Cool, where's the dipole in 2?
The carbon oxygen.
Single bond. Awesome, fantastic. Okay, so would 2 and C work? They match. How about B? Would 2 and B work?
Yes, because they're the same.
Yeah, they would also work. Okay, so the assumption that I was kind of hinting at you was that you're making that it's just a 1-for-1 match. No, not at all. Okay, 2 could also dissolve in B.
Like, but a 1-for-1 match. and
So
then you have
1 is
1-for-1.
not going to dissolve in just one liquid necessarily. 2 is not going to dissolve in just one liquid necessarily. Okay? And I think when you look at a question like this, you jump on and immediately assume there is one correct answer. Okay? The world rarely works that way. Okay? You should not expect your science classes to do the same. Or you should expect your science classes to do the same thing as the real world. It's not always a 1-for-1 match. The only reason you get 1-for-1 matches are contrived situations from your teachers. Your teachers shouldn't be making contrived situations. They should be setting you up with a system that allows you to explain why you're coming up with the comparisons you're coming up with. Does that make sense? Okay. So for this particular scenario, there are multiple correct answers. There's also multiple wrong answers. So if you were telling me 1 dissolved in C, you're wrong. Okay? Because they don't have any of those same intermolecular forces, which is why this kind of question gets graded not based off of what pair you picked necessarily, but what was your explanation for the pair you picked. Okay? Which is dangerous. Okay? But that's how I do virtually everything. I want to know the explanation. What are you thinking about to get to that conclusion? That's what I want to see in those open documents, because that's where I can be like, dang, you're thinking about this wrong. Let me help you get that reprogrammed so you can get to the right system. If you just get the right answer, I don't know whether you lucked into that answer, in which case, are you going to luck into it again on an exam? Probably not, which means your exam score goes down, and now you get mad at me because I didn't teach you anything. Well, I didn't teach you anything because I didn't appropriately assess whether you actually knew what you were trying to do. Okay? So you need to push on that explanation. And if you're going through the homework and you'll be like, I don't feel like I can come up with an explanation, that's a really good opportunity to be like, hey, Mike, I need some help. Where could you get that help?
You.
Office hours. Do you know how lonely office hours are right now? Nobody showed up Monday. Nobody showed up Wednesday.
Monday.
Afternoon.
Oh.
Okay. And that's okay. I understand your schedules may not align. So I fully appreciate that. Okay, but just because our schedules don't align doesn't mean that's a reason to avoid getting help. Okay? That's a reason to send me an email being like, Mike, your office hours suck. Please change them. Okay, what do you want me to change them to? Right? Because me just sitting there twiddling my fingers isn't useful for me and it's not useful for you. Let's find something that works. Okay? And that's not to say either that we are going to find something that works. We may not be able to find something. Okay? But we should at least try. Does that make sense? We good with that? Okay. I know where we're at least that clock, but my clock says I got 2 more minutes. Okay, and I wanted to, come on, work with me. Okay, push a little bit further. We could look at more of a complex system on how the solvents could help change an overall reaction. Okay, this slide is really neat. We will talk about this, not right now. Okay, way too complex to address yet because we aren't confident at all about our reactions or any of those things. Okay, there's other things that we can drop in with, does it dissolve in water? We've kind of already addressed this. Okay, when we look back at that previous slide, when we said, what was it, 2? That 2 could dissolve in B or C, or for that matter, it could actually dissolve in A. There's multiple ways that it could go through and dissolve. Okay, when we go through and look at solubility, okay, does it dissolve in water? There's multiple things that could contribute to that. So it doesn't get asked in a multiple choice, it gets asked in a show your work, because what I'm asking for is that explanation. Okay? So you should have an explanation that explains why you think it should or should not dissolve. Okay? In that scenario, I may very well go through and be like, this explanation is great, I love your explanation. You're wrong, but your explanation is great. That's full points, I don't care. You're showing the proper logic and understanding behind what you're supposed to be evaluating to think about it. Okay? The reality of the world doesn't necessarily match our theory. Does that make sense? Okay. What can be done with these interactions? Okay, because everybody likes to go, oh, yo, you never talk about how it's relevant. Soap. How does soap work? It's taking advantage of intermolecular forces. Okay? And soap is a pretty interesting molecule because if we look at soap, ballpark, I'm a little bit off, but whatever. Okay, we have this portion that is all very protic, or actually it's not protic there in that form. It's polar, and we have this portion that is all nonpolar. So what can this molecule do? This molecule can have the nonpolar stuff stick to all the fats and greases that are also nonpolar, but it can also have the polar part of it stick to the water. So what it acts as is an intermediary to bring the dirt and grease off your hands and into the water so that you can then rinse it off your hands. So intermolecular forces and solubility, soap does this for us. Okay? And if that's not cool enough for you, okay, this type of molecule, that soap molecule, okay, officially this is how it works. It forms micelles. Okay? But we can scale up micelles, those orange parts being all the nonpolar, the white part being the polar part. We could scale this up to things called liposomes or liposomes. Anybody have the proper? Liposome. Okay, see, there you go. The biology side of it, I don't really know it. Okay? Liposomes, that happens in our cells. We can get these things called liposomes that are segregating different parts of cells. If we push even further, okay, we can move to a bilayer sheet. What's a bilayer sheet? It's a liposome that's like 1,000 billion times bigger. Okay? And we draw it straight because if we look at something that's large enough round, when we look at a very small section of it, it looks flat. Kind of like, yeah, there we go, the Earth, if we wanted to bring in all sorts of fun politics around flat Earth stuff. Okay? Same kind of thing can come out of it. Okay? all of those are based off of intermolecular forces and how these things stack, pack, and interact with each other. So everything you address within biology is coming back to these intermolecular forces and how they apply. It's pretty wicked. It's painful at times too, because you can boil it down to such small, simple principles, and yet it helps to explain some pretty gnarly stuff that goes on in biology. Okay? With that, I would like to talk more. I really wanted to get to, wow, dang. I really wanted to get to this slide, but I didn't. We'll start with this slide, and then we'll backtrack into the acids and bases. This slide is coming out of our play posit. Okay? I would argue this is a critical slide. Okay? You need to know this slide. Okay? And we'll push on that further Monday.